All right, perfect. Hello, everyone. Thank you so much for coming to this webinar. My name is Geordie. I'm so excited to be here today to show you how to use Bolt, how you can train really fast with Bolt, even if you have really large networks, the benefits of large sparse models, and also demonstrate how fast we can do inference. To start off, we want to show you how to actually define a network in Bolt. And to do that, we're going to do it with a simple exercise. We're going to do image classification with MNIST. So this data set consists of images that are 28 by 20 pixels in size, and they're images of handwritings of numbers between 0 through 9. And the network is supposed to learn to predict what number is actually written in there. To do this, we're going to use a very simple neural network. We're going to have a 784 dimensional input, that's 20 by 28, followed by a 1000 dimensional hidden layer with ReLU, and also a 10 dimensional output layer with softmax, so that we can choose between 0 and 9. And in the first cell here, you can see how you would define a network like this in Keras. And in the second cell, you can see how you can define the same network with Bolt. We put a lot of effort into trying to make this as familiar and approachable as possible. So as you can see, the syntax is very similar with popular deep learning frameworks. So it should be very easy to transition into Bolt. Now that we have defined our network, we can now train it. We're going to train it with categorical cross entropy loss, because this is a classification task, and we're going to predict with categorical accuracy. That is just how many of the predictions we got correct. And as you can see, we just trained our first network, and we got around 95% accuracy, which is great. We now trained our first Bolt network, but that's not too special, right? Like, you can do this with any deep learning framework, and this is kind of like the hello world task of deep learning. So instead, here we like bigger models, and because bigger models allow us to do more complex tasks. And one such example of a more complicated task is intent classification. Here we're going to demonstrate that with the Clink 150 dataset. Now, this dataset consists of customer queries. So for example, things like, oh, do I have to pay for carry-on on Delta? Right? And then it maps these queries to the IDs of the intentions. So for example, the query that I said before, maybe the intention is carry-ons, and carry-ons might have an ID 42 or whatever between 0 and 150. And so the task here is to predict, given a query, to predict what the unique ID of the intention is. Now, in this case, as you can see here through the input dimension parameter, we have vectorized the queries into vectors of around 5,000 dimensions. And after that, we're going to pass it to a hidden layer of 10,000 dimensions. And finally, onto the final layer, which is 151 dimensions. And if you do the math here, it's a 51 million parameter model, which is pretty big. If you compare this with other deep learning frameworks, it would take about 100 seconds to train each epoch. But here we have a special offering here, which is load factor. Now, if you take a look at the definition for the first layer here, in addition to the dimension and the activation function, we're also defining a load factor. Now, this is a knob that allows you to set your computational budget, so you can harness the power of deep learning for very cheap, really. In this case, we're using 0.05 or 5% of 10,000. So for each input vector, we're only going to use 500 out of the 10,000 neurons in this first layer. And this is not just any 500 neurons. These are the best 500 neurons that Bolt curates for each sample. Additionally, in addition to training with sparsity, you can also do inference with sparsity. And you can do this just by calling a single method, which is enable sparse inference. So in this case, enable sparse inference is basically enables you to use sparsity also in inference. And the difference is one of the benefits of using Bolt to do sparse inference is, since we're also training with sparsity and the network knows that we're going to use sparsity in inference, it really optimizes for that sparse inference. So you're using the same network for both training and inference, which leads to performance benefits. Now, as you can see, each epoch here took only about 3 seconds to train. So if we think about it, this is a 51 million parameter model, while the MNIST network above is only a 700,000 parameter model, I believe. And that also took about 3 seconds per epoch to run. So here we're seeing, because we're using load factor, we're able to have a model that's about 70 times the size of the model before, but each epoch of training runs in about the same amount of time, which is very exciting to us. And as you can see, after 3 epochs, we were able to get the accuracy up to 83%. So yeah, that's very exciting to us. The fact that we are able to scale the model to 70 times as large and still train in about the same time. And now that we've seen how training time scales with the size of the model, we want to show you how you can use even larger models. So in this case, we're going to pivot to a different task, which is sentiment classification. So in this case, we're going to use the Yelp review dataset. So as the name suggests, these are reviews on Yelp that you would have to classify between a good review or a bad review. If you like the taco place, then that's maybe a positive review. If you don't like, I don't know, whatever other place, then that's and you might write a negative review. So as you can see here, to do this task with Bolt, we first vectorize the queries, these sentences into vectors of 100,000 dimensions, which, if you think about it, is quite big. But that's also one of the benefits of natively supporting sparsity. You can imagine you can have so much flexibility with feature engineering, and now you can extract such a rich feature set from each sample so that you only need to train on, so that you can have an accurate model after training just on one corpus. Yeah, so we're passing, so this is a 200 million parameter model. We have an input dimension of 100,000 followed by a hidden layer of 2,000. So that's 200 million. And we were able to train this on a CPU for just a few minutes. But it's still a little long for this demo. So instead, we're going to take this chance to introduce you to our save feature. So in practice, we're going to want to train a model once and then keep using it for inference. So it's really important to have the ability to save a trained model. So we bake that into Bolt. All you have to do to save your model is to call the save method, as shown here, and then you pass in the file name that you want to save it to. And then when you want to load it back, you just have to call the load function. So let's load it here. All right, so we successfully loaded the model. Okay, and as a benchmark, we compared it to Roberta, one of the state-of-the-art NLP models. So Roberta is a 300 parameter. It's around 300, has around 300 parameters, and it comes pre-trained because it takes a lot of data and a lot of computing power to train. In fact, this model was trained on 100 gigabytes of data for a total of 1 month on a fleet of 8 GPUs. And so this is not something that any developer can just train on their own. So in fact, instead, what we do is we download a pre-trained model, a model that has been pre-trained on a more general understanding task like masked language modeling, and then we fine-tune it on the data set of our choice for the task of our choice. And this performs great. However, it is known that you can really get even better results if you train from scratch on the task that you actually want to do. So in this case, we ran it on Roberta and we got around 83% accuracy. And we think Bolt can do better. So let's actually run the prediction API and see how well Bolt does. All right, and we just see, as you can see here, we got 93% accuracy, about 10% more than Roberta did. So this is an example of a use case where training from scratch on the task that you want can actually reap really tangible benefits. As I said before, we really like large models here, so we prepared an even larger model, this time a 1 billion parameter model that we trained on a slightly larger text corpus. It's the Amazon Polarity dataset. And this will allow us to do an interactive sentiment analysis demo. Yeah, so in this case, it's a 1 billion parameter model. We trained it on CPU for only an hour. And once it loads, I'm going to type in some sentences, and it will tell me what sentiment it thinks it is, whether positive or negative, in real time. So to start off, let's go with something very simple, something that is clearly positive. All right, so it managed to get the right result. And now let's try the opposite. Let's say I hate you. All right, and once again, it was able to predict correctly. Let's give it something a bit more neutral, but also contextual. Something like chocolate. And as you can see, it was able to. So from these three results alone, we can see that it's able to capture the sentiment of simple sentences as well as the context from the training data that it learned from. Now, I want to give it something a bit more complicated, maybe something that has both a positive and negative sentiment in the same sentence, but with an overall negative sentiment, like I like chocolate, but it makes me sick. All right, and as we can see, it also managed to get the right answer for this one because it has an overall negative sentiment. So from here, we can see that it's able to learn to understand even more complex sentences. Now let's get a little bit real for a bit here. I like ThirdAI, but let's say I'd rather work somewhere else. And let's see where this takes us. All right. And of course, I'm just kidding. So, and there you go. And there you have it. With this demo, we were able to really get a feel for how well Bolt is able to predict the sentiment of sentences. It was able to predict it for both simple and more complicated sentences. But that's not it. One last thing, we want to talk about speed. So we talked about, oh, right, I have to stop this one first. So let's stop that one. So we talked about training speed. We talked about how we were able to train a 1 billion parameter model on CPU for just about an hour. So now we want to talk about the inference speed. Once again, we're going to compare it to Roberta, which in this case was able to find the sentiment of the sentence "I love chocolate" within 350 milliseconds. So 350 milliseconds, and Bolt did it in up to 6 milliseconds. So that's about a 50 times improvement in inference time. So just to reiterate, we trained a 1 billion parameter model on CPU. We're getting state-of-the-art accuracy, and we're with an inference speed of up to 50 times as fast. This is very exciting for us here at ThirdAI, and we hope you're just as excited about it. And with that, I conclude this demo about Bolt and pass it over to Josh to talk about a document search with MaxFlash. Thank you so much.